We are going to review the quiz for convolutional neural networks. The first question is, natural images tend to have inherent translation invariance. What does translation invariance mean? You guys are looking at my picture? Look at me. Do I change if I go like this? Am I the same person or am I a different person now?
Same.
The same person. That is, in other words, as I move across horizontally on the screen, I remain the same person. So images, the objects in the images, they have translation invariance, isn't it? If you move them from one part of the screen, a picture, to another, they would still be the same thing. A house will remain a house and a cat will remain a cat. You don't expect a house, when it goes to the upper corner of the screen, to morph into a cat or things like that. Isn't it? So that is inherent translation invariance. Natural images have that. Next question is, min pooling applied to an image tends to pick the darker feature. See, if you are picking the smallest value in a window, which is min pooling, what will happen? Suppose you use it when the background is white and the features or the drawing is in dark. You realize that you want to pick or see the pixel wherever it is dark, right? The features are in dark. Somebody has made a sketch in dark on a white background. So that is when min pooling works very well. It picks the darker features from the image. And then if you just apply it to an image, let's say a flower or something, what will it do? For every 4 pixels, it will pick the darkest of them, right? And because it picks the darkest pixel, the darkest value, it will tend to darken the picture, isn't it? So that is what min pooling does. Oh no, there's a grammatical error. Giving and min pooling. Would you mind, guys, if I fix it now, because I won't get a time to fix it later?
Might as well.
Yes, thank you. Given a min pooling window, when it is applied to a region of the input, it picks something. We'll find out what it picks. Yeah. Given a min pooling window, when it is applied to a region of the input, it picks the minimum of the value is visible within the window. It is literally by definition, right? So that's that. Min pooling, oh wow, all the min pooling questions are together. Min pooling works best for, obviously, images with a dark white background. Because if the bright things don't matter, it's the dark thing that's matter. That is the case when you have a white background or a very bright background. Given a max pooling window, the opposite of this, when it is applied to a region of the input, it picks the maximum of the values visible within the window. Literally by definition, isn't it? Next is, consider a convolutional neural net with 10 filters applied to a color RGB image of 64 by 64. Each filter is a 5x5 filter. Now, determine how many trainable neural network parameters are associated with the image. So the only formula in CNN that you need to remember is that, you know, the n plus 2p minus f over s plus 1, the floor function. That's the only formula that I gave you in notes to be there. So here we have a filter is of length and width this, channel is 3, therefore there are 75. Each filter is of length this much. So in fact, in this particular case, you don't even have to look at the output image. Sorry, this was a trick question. Most of the information is useless. You just have to look at the filter. If the filter is 5x5, right, then you have, and 3 channels, so you have 75 weights per filter, and each filter has a bias. And so you have a bias term, so it's 76. And now there are 10 filters, so there's 760. In a deep learning CNN is an acronym for convolutional neural nets. Of course, I hope none of you believe that it was your completely neurotic neighbor. So next is, after the input has gone through the convolutional layer, the output is flattened before being fed into the fully connected layer. The reason for this is, and the real reason is, the dense layers can only take a one-dimensional vector, isn't it? So for a min batch, the convolutional layer produces four-dimensional tensor, height, width, channel, and batch size, whereas a feed-forward network expects a two-dimensional tensor, feature vector, and a batch of them, isn't it? That's how neural networks work when you're passing in mini batches. So mini batches are the extra dimension that always stay. But think intuitively, your image is a three-dimensional object. It needs to become one-dimensional. So from 3 to 1 dimension, but then if you add the batch size, it will become from 4 to 2. Right? So that's the answer. Next is, consider a convolutional layer with 10 filters applied to the same problem. Right? Assuming that we are using the same padding. What is the same padding formula? When do we use the same padding? What does same padding mean?
It'll have the same shape.
Yes, the output must have the same shape as the input. Right? Number of channels may change, but the shape has to remain the same. Height and width have to remain the same. So each filter is a 9x9 filter, 9x9. So if you want to have the same size, assume that we are applying a max pooling of size 2, right, which is a standard, then what can we say about the output size and the number of channels? So you realize that if you're using the same, the output before the max pooling has to be 64 by 64, isn't it, guys? And then max pooling is going to decrease it by a factor of 2. And so height and width will become 32. Right? How many filters are there? There are 10 filters. So there are 10 output channels. Is this making sense, guys? Think about it this way. Before you apply the max pooling layer, the same padding ensures that input and output are the same. Input is 64 by 64, so output is 64 by 64, right? And how many filters are there? 10. So obviously there are 10 channels now. And now, once you put it through max pooling, what will it do? It will cut the height and weight in half, right? So it becomes 32, 32, and 10 channels. So I've given all the details here. The same padding automatically implies that the output size from the convolution would be the same as input. So it will be this. Since there are 10 filters, therefore the number of channels in the output are 10. Max pooling, a pool of 2 is a filter, and so the stride is 2. Therefore, applying the same formula as above, we get a final output of half. 32, that's that. Successive convolutional layer tends to have an increasing number of output channels, isn't it? What happens to the image? You tend to have smaller and smaller images. The input to the successive layers, the outputs become smaller and smaller, right? From 64, you finally go to maybe 4 by 4. But the number of output channel keeps increasing. This happens everywhere. Can you guys point to an exception to this? One exception to this is the generator of the GAN. Remember, in the generator of the GAN, you run a convolutional neural networks backwards, isn't it? Do you remember, guys, that in a DC GAN, not any GAN, what am I saying? In a DC GAN architecture, the generator is a convolutional neural network run backwards. Anybody remembers that?
Yes, Asif.
Yes.
So
Yes,
does that
sir.
process still mean it's convolution?
Yeah,
Or
you
is it
actually people
deconvolution?
call it deconv. They call the operations not convolutions, but deconv operations. Right. So that's Some people, I mean, depends. Language there's a bit loose. I've heard even people call it. I don't know how correct it is to say that. They call those things a decon. Let me take a decon network or something like that. They'll say. Location invariant feature extraction is a property of which of these neural architectures? Recurrent, convolutional. This I hope is a no-brainer, right? The whole point of filters is that it will detect your edge no matter where in the image it is. So it does location invariant feature extraction, right? Which is one of the great strengths of convolution. The convolution operation is, by the way, this is also something I may just put as an aside. Convolutions are not the only things. We are beginning to realize that transformers have a similar property. If meaning-wise two things are related in a sentence, you change the sentence in such a way that you preserve the meaning, those words are still remain related, even though their positions have changed. So to some extent, this property seems to belong to transformers also. Convolution operations are considered in deep neural networks. The operation as considered in deep neural networks differs from the mathematical and signal processing definition of the convolution operation. So the choices were false. Cross correlation has nothing whatsoever to do with CNN. That's totally wrong. In fact, what we do, mathematicians would call cross correlation. Another false. Signal processing folks have it backwards. So one claim is that we do convolutions, the other guys do it wrong. The third is that, well, it is true. We lose an amount of accuracy too, and darn the mathematicians. That's not true. The convolution of CNN matches the mathematical definition of convolution. That's not true. See, we don't do that, inversions. So, but it really doesn't matter. It's true that we are not strictly the convolution operation, but the little extra bit needed to make it the strict convolution definition is unnecessary, especially because of the translation invariance property of the filters. So true, but it really does not matter since the extra operations to make it strictly correct brings no added advantage. So why not save those operations? Next question. Activation functions are not necessary for convolutional neural nets since the main mechanisms are the convolution operations and the pooling operations. True, false? False. If you don't activate, you don't get nonlinear deformations. Max pooling applied to an input image picks the brighter highlights because you pick the maximum pixel, maximum value in a box, in a window. Consider a convolutional layer with 10 filters applied to a RGB of 64. Same problem. Assume we are using same padding in the input in a stride size of 1. Each filter is a 7. What is the padding size to be input? So this is the formula of the padding size, f minus 1 over 2. We did that in our notes. If we use it, so the answers are this 3. Namely, this. Oh, there is a typo here. Why does it also say 1? I don't know why the correct answer. Maybe there is a bug in the way I wrote the question. Is it a multi-choice question? Hang on, let me go fix it in case I screwed up. One answer only. This looks okay. Okay, I don't know why it is misbehaving like that, but we'll leave it. Next question, the images with the white min pooling works best. Let's go. Okay, we have to go much further down. Okay. Question 9, the same padding. We did all of that. Question 10, successive convolution layer tends to have increasing number of channels. I think we did all of that too. Really doesn't matter. We did this. Convolution operations. 14, max pooling applied brighter. Consider convolutional, this is it, formula applied application. A ReLU activation function cannot be used in conv, etc. Of course it can be used. And ReLU does introduce nonlinearity. So that statement that it fails to introduce nonlinearity is not true. Right? So this is wrong in both counts. Considering max pooling and average pooling, which of the following statements are generally true for images with dark background. Max pooling tends to outperform average pooling, isn't it? So consider that in a convolutional layer, we are using a kernel size of 5 and a stride of 1. What would be the appropriate padding size to ensure that the output of the convolutional layer is of the same thing? Once again, just use that f minus 1 over 2, right? So 5 minus 1 is 4 divided by what is it? 2 will give you 2, right? So there we go. Consider a convolutional layer. See, this all comes down, everything, you realize that comes down to this formula. If you can remember this formula, this is all you need to know to do convolutionals, right? So remember this formula that I gave in class. Consider a conv-net with blah, blah, blah layers, etc. I wouldn't go into it. If you plug in the formula, you will see that this is what comes out. It's just a direct application of that. Convolutional neural networks can be applied to data sets pertaining to, well, images, video, audio, natural language processing, and other types of data. It is surprising how effective CNNs are. People often think that it's only applicable to images and videos. No, it's applicable to audio. It's applicable to words. Sometimes people are surprised that you can use convolutions for natural language processing. And we will use that in this workshop. Fully connected layers in a conv-net usually follow the convolutional net. So, fully connected layers are the end. So first you do feature extraction, then you vectorize it, you make it into a one-dimensional vector, and then you feed it into the dense layers. That is it. So the purpose of the first part, the convolutional parts, is to do the feature extraction. The part of the second one is your classification or whatever it is that you want to do. Given an average pooling window, when it is applied to a region of input, it picks the average of the value. This is by definition. Which of the following neural architectures is modeled after visual mechanism of living organisms as we understand it? CNN. CNN was discovered by studying the brain, the way the brain of a cat responds to big images. Average pooling applied to an input image smooths the image. Obviously, you take the average. Right? Average is a smoothing operation. Compared to a fully connected layer in a neural network, the convolutional layer in a neural network tends to have far fewer trainable parameters, isn't it? Why? Because the same filter goes all over the image. So so that's a big deal people make about it, that in some sense it is doing parameter sharing, okay, between the neurons, if you think about it. But that is what it is. It has far fewer. Is there any doubt about this, guys? We see that. Yeah? A typical convolutional layer will have like 760 parameters that we just saw in a previous example. Whereas a typical dense layer will have something like thousands and thousands of parameters, tens of thousands of parameters. Right? So for example, if you come from 512 layer to 512 layer, you're looking at, what is it looking at? You're looking at 250,000 parameters approximately. 250,000 parameters. Massive number of parameters, isn't it? Whereas here is 760, much smaller number. And that is it. Oh, that is it. Only 20 questions.